Mr. Abbott, I'd like to go over and review this Path of the Sun worksheet with you. Now, the first thing I'd like to remind you of is if you know the date or the type of season, you've got to know exactly where sunrise and sunset should be. So, the easiest one to start with is always the equinox. You know that on an equinox, the sunrise is due east and the sunset is due west. So if I'm attempting to draw the path of the sun, this is going to be for 41 degrees north, which is probably somewhere in New York. I like to plot sunrise and sunset first. I always like to start with the equinox. So I'm going to say sunrise is due east and sunset is due west. If I was going to do the winter solstice, since the vertical ray is the sun is south of east, south of the equator, this is going to be south of east to south of west. On June 21st, okay, since the vertical ray is north of the equator, then you get north of east to north of west. So we're looking at the path. Sunrise is somewhere towards the eastern horizon, sunset is somewhere towards the western horizon. Now, the exact altitude of the sun depends on the season or what date it is and your latitude. Okay, each season, because the vertical ray of the sun shifts by 23.5 degrees, you know that the altitude or the angle of the noon sun also changes by 23.5 degrees. So the first thing that we have to do is, if we're going to draw all three paths of the sun, is we have to calculate what the equinox path is. The equinox is the easiest one to do. So on the equinox, the vertical ray of the sun hits the equator. All right, so over here, right in the middle of this model, I'm going to write 0 degrees, and let's say we start with spring. Okay, 3:21, the vertical ray of the sun would hit the equator. So the sun would be making a 90-degree angle at the equator. Okay, so the angle of the sun is 90 degrees at the equator. Okay, you have to find your latitude, which in this case we know is 41 degrees north, and subtract that from 90. So New York is 41 degrees away from the vertical ray. I do 90 minus 41, and that would give me 49 degrees for the noon sun on the equinox. Now, if I'm in the northern hemisphere, we're an observer up here at 41 degrees, so we would have to look south. So when I plot the noon sun, I do sunrise, sunset, and right at 49 degrees, I'm going to plot the noon sun. In the morning, the angles would be getting higher, and your shadow would get shorter. So that would be sunrise to solar noon. The altitude increases, and then from noon to sunset, the altitude decreases. So I'm going to label this path, the path in the middle, is definitely the equinox. Now, for the summer solstice, the vertical ray now shifts north. So for the summer solstice, the sun is now shining directly at 23.5 degrees north, so the vertical ray shifts closer to our observer. That means we're going to see the sun appear to move up by 23.5 degrees. So to get the summer solstice, we add 23.5 to the angle for the equinox. So now I do 49 plus 23.5, and when I add that, this is going to be 0.5, this is going to be 72.5 degrees. So summer solstice is June 21st. Sunrise is somewhere north of east. This is on a little bit of an angle, so I go directly across and I get sunset north of west. So I plot sunrise, sunset. The angle I'm looking for is 72.5, so I do 70, 71, 72, and I'm going to put a dot exactly in the middle. So the highest angle is going to be solar noon. It rises in the east and it sets in the west. Now, it almost appears like these paths are crossing, but they're definitely not. All right, this is a flat two-dimensional model. In reality, these are arcs across the sky. Now, the vertical ray of the sun would start to shift south after the summer solstice. That's the summer sunstop. It would hit the equator again on 9/23. 6 months after the summer solstice, we would reach the winter solstice. So the vertical ray of the sun would hit 23.5 degrees south on 12/21. So for 6 months, the vertical ray moves south. Sunrise moves south for 6 months. And then you hit the solstice, the sun stop, and it reaches the lowest angle for the year for us. Okay. So from the equinox position, you're now moving the vertical ray 23.5 degrees farther away. So for this, for the winter solstice, which in New York is 12/21, I'm going to take my 49 degrees and I'm going to subtract 23.5. If you need to, you could use your calculator on this one, but 49 minus 23.5 gives you an angle of 25.5 degrees. So each season, no matter where you are on the planet, the vertical ray shifts 23.5 degrees, okay, from winter back to the spring equinox. It would start moving north again. So if I plot my winter path, it rises south of east, it sets south of west, 25.5 degrees would be here, and winter gives us the shortest, lowest path for the year. So I'm going to mark this one as 12/21, that's the winter solstice path, and this one would be 6/21. Now, if I change the number for the latitude, you need to be able to modify it and figure out the angles. If I move 10 degrees closer to the equator, that means that every single one of these angles would move up by 10 degrees. If I moved to an even higher latitude and I moved farther from the vertical ray, all of these angles would shift down. But that's essentially how you do the path of the sun.